Hello and welcome back. In the last video, I was discussing how to define probability distributions and um, how to calculate average values um, from those probability distributions. And just to remind you, I had this example where there were some student scores and there's a graph kind of like this, where the outcomes were 50%, 60%, 70%, 80%, 90%, and 100%. And there were two students who scored 50 and 100. There were five students who scored 60 and 90. And there were seven students who scored 70 and 80. And what we calculated, so we did that, and we defined a probability of distribution for the ith score, 50 through 100. That would just simply be the number of students who scored that amount divided by the total number of students, which in this case would be 28. We'll just call that capital N for the total number. The average score as we would calculate any average is simply you sum over the random variable. In this case, it's discrete. Then next time we'll have random variables which are continuous, and these sums will be replaced with integrals. And you multiply by the thing you're trying to average, which in this case is just the score itself, but it really could be anything, and I'll elaborate on that here in a moment. And then the probability of that score. So in this case, my probabilities, as I'm writing, I better write these down here because we'll need them. The probability of 50 is 2 over 28. Probability of 60 is 5 over 28. Probability of 70 is 7 over 28. Probability of 80 is also 7 over 28. Probability of 90 is 5 over 28. And the probability of 100 is 2 over 28. And what those probabilities are telling us is that if we were to just grab a student at random and ask what score did you get, 7/28 of the time you'd see 70, and 5/28 of the time you'd see 60, and 2/28 of the time you'd see 50. Okay, and so from the graph we can see it's a symmetric distribution. The average score is going to be right in the middle, so the average is going to be 75. And sure enough, if we go through this and evaluate this sum, we would get 50 times 2/28 plus 60 times 5/28 plus 70 times 7/28 plus 80 times 7/28 plus 90 times 5/28. Sorry, it's a little repetitive here. Plus 100 times 2/28. So if you add all those up, sure enough, and we saw that in the last video, you get 75. So the average score would be 75, which matches visually what we see. Okay, so that's how we use probabilities to calculate expectation values or averages. You simply take the thing you're averaging and kind of sum over all possible outcomes of it, multiply it or weighted by their relative probabilities. And that's how you calculate an average value. Very good. Now, another concept which appears in addition to averages is the idea of a standard deviation. Okay, so the idea of a standard deviation is to measure, on average, how far are things from the mean. So if we look at our distribution we had before, I'll just kind of sketch it like that. Okay, we had the averages right down the middle at 75. However, it's not like everybody scored 75. There was a spread around that. That's the concept of standard deviation. So what you would want to do is look at how far from the average are the different outcomes. So you would want to measure the distance, and we want the distance, not, so we want to get rid of minus signs. So it could be the standard deviation could come from either underperforming or overperforming students in this case. So we need some sort of a quantity which measures that. You want it to not be negative because we don't want pluses and minuses to cancel out, because like in this example here, if the pluses and minuses cancel out, we're going to say that basically there's no spread. Well, that isn't right. Visually, we see that there's a spread, so we can't let them cancel out. So the way we do this is the following. We find, what we really do is we calculate the difference of each outcome from the average. We square that and average it. So it's the average of the distance squared. And then after we're done, take the square root. So standard deviation is defined as this. Sigma, sorry, let me go back to black here. Say there's some quantity, let's call it F, okay? So for some quantity, call it F, okay? And the different outcomes based upon score or any whatever the random variable would be F sub I. So kind of the quantity is F, and then F sub I would be the different values it could take. The average value for F we found is just as before, the sum over F sub I times the probability of I. That would give us the average value. And we're going to define a new quantity called the standard deviation, sigma. And what we actually do is we first calculate sigma squared. And I'm going to label it with an F. So this will be the standard deviation of F in a data set. And that is simply, we can write it in a couple different ways. It is the average of F, parenthesis there, minus the average of F squared. So look at what that's doing. So there are many different values that F can take. There's only one average value. So what this is doing is finding the distance between any specific value and the average and squaring it to get rid of the minus sign. And then doing that for all, finding that distance squared for all of these points and averaging that quantity in the usual way. And then ultimately, we can take the square root of F, or of this formula to find sigma equals the square root, of the average of F minus the average of F. Sounds tricky when you write it, when you say it, but you have to unpack the different definitions. So that's the idea of standard deviation. Let's see how it is applied. Let's take the example of the scores, student scores. Let's find the standard deviation, the scores. Okay, and we're first going to find the standard deviation squared. The way you would do that would be to calculate. So we want the average of the score minus the average score squared and averaged. So, well, we already saw this. The average score was 75. So everywhere I have that, that's just 75. Now to calculate the rest of it, then I would have to say this is, well, there's an averaging. So it's going to be the sum over outcomes. And I'm going to write the probability part first here. Times, and it's score, the ith score minus the average score squared. So that's going to be I minus 75 squared. So this would be the average of the distance from each score takes from the mean score squared. And so we have to calculate that and take the square root. So that would be, oh, let's go through it here. That's going to be 2/28 times, for the case of scores, equal to 50. That's going to be 50 minus 75 squared. So that's going to be 25 squared plus 5/28. Now we're talking about when the score is 60. So that's going to be 15 squared. Notice how the minus signs go away by squaring things. Plus 7/28 for the score of 70. And then for 80, it's going to look like the same. And 90 will give us a 15 squared, and 100 will give us a 25 squared. Oh. Okay, so now we have to type that in the calculator and see what we get. So typing all that in the calculator, I get roughly 182.1 plus a bit more for sigma squared. And so therefore sigma, which is for the scores, so you take the square root of that result, and I get 13.5 roughly. So if we look back at our data set, and we see, okay, well, the average is right here in the middle. And if I was going to estimate a typical deviation away from that, I would see, well, okay, this here, this one's close. This one's a little farther away. This one's quite a bit farther away. However, a lot more students score these closer ones. So you'd expect it to be something like, oh, I don't know, something like 15, just eyeballing it. But so the fact that it came out to be 13.5, that seems very reasonable. So the kind of typical width of the distribution is 13.5 in this case. Okay, so that's how that can be used to calculate things. An interesting aside is you can show that the following is true. In fact, this could also be taken as the definition of the standard deviation. Sigma squared equals, remember I said it was the average of f minus the average of f quantity squared. Now, you could expand this out and write this as the average of f squared minus 2f times the average of f plus the average of f squared. And if you think about it, since averaging is just computing sums, which are linear, you can distribute this. So this becomes the same as the average of f squared in the first term minus 2 times the average of f times the average of f plus the average of f squared. We're almost done because I know this looks like we've got a lot more averaging to do, but in reality, once you see the average of f, that's just a number, like 2 or 3 or 4. It's just some number, which means it pulls out of the averaging of the indicated by this bracket. So I could rewrite this to be f squared minus 2, the average of f squared. Basically, just factor this out, and you get average of f times average of f, plus the average of f squared times the average of nothing, or the average of 1, really. And that's just 1, because the probability distribution is normalized. And so we can rewrite this to say that the standard deviation for f can also be written as the average of f squared minus the average of f quantity squared. So for the first one you put the square before averaging, second one you square it afterwards, and that will give you the standard deviation squared. Just an aside, this term where you take the object itself and square it, it has its own name. This is sometimes called the RMS. Well, I'll tell you what, I'll go to the next slide, next page, and we'll see that. So there's a very closely related quantity called the RMS value. And it's sort of like standard deviation, but just a little different. So the RMS, which stands for root mean squared. And what that is the square root of the average of f squared, the root of the mean of the square. And it's sort of like standard deviation. In fact, if the average value of f is 0, they are identical, but it's just another term that comes up a lot, the RMS value of something. For example, when we talk about voltage, in our house we have AC voltage. The voltage swings up and down, and so the average value of the voltage is actually 0. So when people are talking about say 110 or 220, what they're getting at is the fact that it's not that the average is the average is 0, but if you were to calculate the average of the square of the voltage, it wouldn't be 0. Now, in fact, I believe the 110 and 220 are actually the peak voltage numbers. So, but you could characterize things by an RMS value if you wanted to. So anyway, very good. Next time, we're going to calculate average values and probabilities for a couple continuous distributions. And then we will use all this math for calculating physics quantities.